All right, and then once this goes live, I'm going to just do a quick sound check here on my phone to make sure sound's coming through. Get the chat up, make sure this is all working. Don't see it yet. So weird. All right, it's up now. Okay. All right, so sound is working. Alrighty, let's go ahead and jump into it. Alrighty, welcome to week 3 of the CAD class. You'll notice on my screen that I managed to actually change both places where it says week 3 to say week 3 instead of, last week when I forgot one of them. All right, so we're gonna go back to our normal format after last week where we did the COTS parts first and then the engineering concept. Here we're gonna start with the engineering concept, which is the way we normally do it, and then we'll do COTS after that. So this week we are talking about torque and moments, which is a pretty simple but important concept. So the first thing we need to talk about is what is torque. And torque can be a little bit kind of like hard to like describe in very precise terms, but basically it is a rotational force. If you think about twisting something, like what is that? What is that force that you're applying? That's torque, right? So a couple examples here, like if you're unscrewing a tight bottle cap, like you're applying torque to the bottle cap to unscrew it. If you're driving something with an electric motor, right? The motor is applying torque to turn the shaft, or you torque bolts to tighten them or loosen them, frankly. So that's torque. So basically, how is torque measured, right? Like how do you describe how much torque you have? So there's a symbol. It's the Greek letter tau, or however you pronounce that. This little like curvy, fancy looking T thing. Um, that's pretty standard. I will say some of the symbols that I use, there's going to be a few equations in here. Don't everybody leave the chat, but there's going to be a few equations in this little presentation. Some of the symbols I use are not really standard. I just kind of threw some variables in the equations that are, kind of intuitive. But you might see you might take other classes, or you might see other equations and stuff on the internet that use different variables. So don't get confused if that's the case, right? The important thing is the relationship between the variables, not really what letter I use. But in the case of, this symbol is standard for torque across the board usually. So torque is measured with a compound unit. You guys are probably familiar with compound units from school. A compound unit is like when you have, if you think about like miles per hour, right? That's a compound unit. So torque is a different compound unit. It's a little bit of a weird one, but because it is, there's no division in the compound unit. It's the product, right? It's the multiplication of a distance and a force. Right, so I've got some examples down here. So like foot-pounds, right? That's feet multiplied by pounds. And the thing is, because the multiplication is commutative, you can reverse which way it is, right? So it can be foot-pounds or pound-feet. It doesn't matter, right? It's the same thing either way you flip it. You will hear people say it different ways, and you will see it written different ways. The thing that's important is that they're multiplied together. The direction that you multiply it doesn't matter. So foot-pounds is a really common one. You guys have probably heard that before, like car engines and stuff. People usually talk about how much torque they produce in foot-pounds. Newton meters is a common one. That's actually the like standard metric measurement. I mean, I use Newton meters for pretty much all the math that I do, because it's the metric unit. It's the easy one to use when you're doing physics calculations. A lot of motor data sheets and stuff that we use in FRC give the torque in Newton meters, so Newton meters is a good one to use. Inch ounces is another one. There's also inch pounds. There's a lot of different ones, but the key thing here is that they're multiplied together, and any unit of distance and any force will work. And you'll notice here, when we're talking about ounces and pounds, we're talking about pound force and ounces force. That's a little bit of a weird distinction when it comes to standard units as opposed to metric, because standard uses the same units for force as it uses for mass. And so there's a little bit of a weird thing. You have to specify that you're talking about pounds force, not pounds mass, because they are different things. Okay, so let's talk about what a moment is. And I'm not talking about time. There's no time at this. Moment is a term in physics, and it's basically the product, the multiplication of some sort of physical quantity like force or mass or something like that, and then a distance, right? And the distance is kind of describing like how far away the force is acting from something important, right? And that's kind of a weird description, and I'm really not going to go into any detail because that the moment part of this is not really that important. The thing to understand just though is that torque is a moment. There are other types of moments in physics. In engineering, I don't know. I'm trying to think if there's any other moments that are really important to be aware of, and I'm not thinking of any off the top of my head, but torque is definitely the most important one. In physics, there are others that you might need to worry about more. But so when we talk about a moment, right? We talk about some quantity. In this case, it is force, and it's acting as a distance from a pivot, right? In the case of like think about a shaft, right? That's pivoting. Like how far away from the center line of that shaft is the force acting, right? Or think about it like a wrench or something, right? Like you're applying force to a bolt at a certain distance away from where that bolt pivots around. And so that distance is very important, and that distance has a name. It's called the moment arm. You will probably hear people call it that sometimes. Every once in a while, you hear somebody shorten. You'll hear people shorten moment arm to just moment, which is like technically incorrect, but you'll see that a lot. So that's just something to be aware of. When people say moment, they often mean the moment arm. And so I assume this diagram is relatively self-explanatory. We have this kind of like invisible distance here that we're applying a force to, and we're applying the force perpendicular to this kind of line here. This doesn't have to be perpendicular. We're going to get into the special cases where this isn't perpendicular later. But this is the moment arm. So another thing that's going to become important later, this little note that I have here, the key thing is that you need to think about force as a line, right? Force is not a point, right? Force is not a point. Force is a line, right? It's a vector basically, and you got to kind of think about this line as being like infinitely long. It's stretching all the way off my screen in both directions, and so basically all you're measuring, the moment arm, is you're basically just measuring the distance between the force line and the center point of your pivot. All right, so let's talk about the equation, right? We know how to measure torque. We know kind of what it looks like. We know moment arm is kind of important. We know force is important. So the equation is really simple, right? You just take the force and you just multiply it by the moment arm. Here I'm using R to represent the moment arm. Like I said, these variables are not particularly standard. But R is the distance from the pivot up to the place where the force is applied, or the distance between the force line and the pivot. So let's do a quick example. One of our team members is tightening a bolt with a wrench. You're pushing on the wrench with 10 pounds of force. You're pushing exactly perpendicular to the wrench. Your hand is 6 inches from the center of rotation of the bolt. How much torque is applied? So we've got 10 pounds applied perpendicular, and it's 6 inches from the center. So let's go to the next page. We have our equation here. So it's just you multiply the two together. 10 pounds applied 6 inches away, exactly perpendicular, which is when we can use this equation. If it's not perpendicular, you can't use this equation. 60 inch pounds, right? And you could convert, if you wanted these in different units, if you wanted these in Newton meters, or you can convert 6 inches to meters and 10 pounds to newtons, or 10 pounds force to newtons, and then you'll get, whatever this is in metric. So you can obviously convert between these units pretty easily. So you're applying, anyways, in this example, you're applying 60 inch pounds to the bolt. All right, so let's do another one here. You have the same situation, right? You're pushing on a wrench, you're perpendicular to the wrench, but you move your hand a little farther away from the wrench, right? You need to get more leverage, right? You move your hand from 6 inches out to 8 inches, and you're still applying the same amount of force. So Pretty simple. You just multiply them together again. 10 pounds this time times 8 inches, you get 80 inch-pounds, right? And that kind of describes like what you guys probably know from personal experience. If you are trying to tighten a bolt or get a bolt loose, you need to get farther away from the pivot, right? You need to apply more torque. That's what actually matters, is the torque on the bolt. But in order to accomplish that, you can only pull or push with so much force with your hands, but you can increase the torque by increasing your distance from the center, right? That probably measures up to your guys' everyday experiences in terms of how that would work. So this is kind of the mathematical reason why that happens. All right, so let's talk about an angled force line. Now the thing to talk about here is I mentioned earlier that the thing it's important to consider force as a line, and the moment arm is really the perpendicular distance between that line and the pivot, right? But like in the real world, it's not necessarily so obvious like what that distance is. So it's easier to think about it like the diagram that I have here, where you've got this kind of like maybe a physical lever arm, like you think about if you're in a tight space and you've got this wrench, right, and you're pushing on it at kind of a weird angle, or maybe a little bit more realistic one is like, this is a kind of a lever on our intake, right, our intake mechanism. We'll talk about this a little more later, but um, and this is an air cylinder that's pushing on here to actuate the intake or something, right? And you don't necessarily know where the force line is just right off the bat. You know where the pivot is, you know where the air cylinder connects, and you know kind of which direction the air cylinder is pushing. This angle in this diagram here. So um, this is a little more, I guess, common and easy way to think about this setup. And so if we go to the next page, I've got a little better diagram, right? What we actually care about is if we continue this force line across, like infinitely in both directions, we want to know this distance here, which is measured perpendicular to the force line, right? So this is kind of just, I hope these diagrams kind of help explain what we're talking about when we're talking about like measuring the perpendicular distance between the force line and the pivot, because that's what actually matters. Like if I take this line and I stretch it way out long and lay it down super flat, like making this line longer doesn't matter if this distance here doesn't change, right? If I make this line longer and it's out here, right, like this kind of thing, but I'm still pushing it the same distance, the force line is still the same distance from the pivot, I'm still applying the same torque to the joint. And that's a very important thing to understand. And if you can kind of envision force as this line, it gets a little bit easier to kind of understand like some mechanisms on our robots where this setup matters. So let's talk about an equation here. Keep in mind this angle theta here. We're measuring from the side that force is applied on, right? Like if you flip this around and you accidentally get this angle over here instead of this one over here, the equation's going to work differently. And this is the equation here. You'd have to use like cosine, I think, instead. I haven't actually worked out that. I'm pretty sure you'd use cosine. But so, anyways, this is the equation. A little bit of trigonometry. You need to know this angle theta. Like you could pull it from CAD or whatever. But it's basically just the radius or the distance, right? The moment arm r is just the length of the lever, right? Which is this guy right here, which is like the physical part of your assembly. The length of that lever times the sine of the angle theta, right? And so then if we just take this little bit of the equation, replace it with r in the original equation, which was just F times r, then basically we get this equation here, which is still pretty simple. We just have to use our calculator or whatever to figure out what the sine of the angle is. So figure out what the angle is, however you need to, then find the sine of it, and then just multiply everything together, and you're good to go. So let's do a little example here. So kind of what I was talking about before. If we have an air cylinder and we have like a little lever arm on our robot that's 2 inches long, and let's say the air cylinder has 50 pounds of force, and there's a 45-degree angle between the air cylinder and the lever. And that's like this case, right? This is 45 degrees, got an air cylinder here pushing with 50 pounds of force, and this lever arm is 2 inches long. That's what we've got here. So let's just plug those numbers into our equation. It's pretty easy, right? This is our original equation here. We know, the three variables: 50 pounds for the force, 45 degrees for the angle, and 2 inches for the length of the lever arm. The sine of 45 degrees is 0.7071, and so on and so forth. And then obviously we just multiply these all together, and we get 70.71 inch pounds. Right, and we could, like I said earlier, we could do unit conversions. We could convert to millimeters or meters, and we could convert to newtons or whatever, and then we get metric units. But yeah, so that air cylinder is exerting, um, 70 pounds of force, 71 pounds of force ish on that joint, or sorry, inch pounds of torque. I said force, I meant to say torque, on that joint. Now, something else, like I don't have a slide for it here, but like let's talk about real quick. If the air cylinder were not at an angle, and instead was, find my other diagram here, was at a 90-degree angle, right? And the lever arm is 2 inches, right? The moment arm would be 2 inches, and instead of having this sine of 45 in here, it would just be 50 pounds times 2 inches, and then we'd have 100 inch-pounds of torque. And so basically, if you've got a little lever arm on your robot like that, you get more torque if the cylinder is acting perpendicular to it. And so that's kind of important when you're designing like an intake or something. Like, you want to maximize the torque that a small air cylinder can produce, right? You don't want to use a giant air cylinder that's super heavy. You want to use a small air cylinder and get nice leverage to move the mechanism. And then obviously as the mechanism pivots, that the angle changes, right? So you've got to kind of balance out, where the cylinder is pushing as it travels through its stroke. We're going to talk about this a little bit more later. We have a project in how to design a pneumatic joint like that. But we talked about a lot about air cylinders on intakes in terms of why this is useful. There's also things about like arm mechanisms. We think about like pushing on an air cylinder, or pushing on a wrench or whatever, or pulling whatever. But the force can also be due to gravity, right? The force can be the weight of something pulling straight down, right? And you want to know, if I've got a big heavy arm, right? I want to know like what the distance from the center of gravity to the pivot of the arm is, and how heavy the arm is. I can calculate how much torque that arm is going to take to lift, and then I can use that to design a gearbox and design power delivery to basically move that arm in a way where I know that it will be able to lift the weight. We also have to lift our robots a lot of times with like a winch. We have to wrap a cable around a drum or something and lift our robot. And so we can think about how much torque is on that winch by how much tension is on the cable when our robot's hanging on it, right? Like the weight of our robot, 120, 140, 150 pounds, whatever it is. How far is that force line of that cable from the pivot of the drum, and like how much torque is that? And so we would use these equations to figure out, same thing, like how much of a gear ratio do we need to get our climber winch to lift our robot, right? Pretty straightforward. We're going to use some of these concepts a little bit later in the CAD class for some of our design kind of, I guess, projects, it'll become a little bit more obvious where you use this stuff. But do you have any questions? Alrighty. If we don't have any questions, you guys can always ask me later if you do. Also, my thing is like super. There we go. All right. All right. Let's move on to the next one here. So we're going to talk about COTS parts. Remember, that means commercial off the shelf, basically just parts that we buy. Let's check chat real quick, make sure I didn't miss any questions here. Nope, looks pretty good. All right. So we're going to talk about shafts, hubs, and bearings. These are pretty important on our robots. We're going to use these a lot. These are pretty like low level kind of components that you're going to use all over the place, and so it's good to have a good understanding of what the different terms are, what are the options, right? What's available. So we're going to talk about some of the common shafts, hubs, and bearings. So we're going to start off with shafts because that's the key concept here. A shaft is basically a rotating bar that supports or transmits torque to another part of a machine. That or is important, right? Supports or transmits. Maybe it should be and or. Supports and or transmits, right? It can be one or the other or both. Typically, there are exceptions to this, but typically it rotates along with whatever the shaft is driving, right? You think about a wheel or an arm or something that rotates, right? A roller or a winch or a belt or something, right? It rotates along with whatever it's driving. It transmits torque to or from the component, right? It can take torque out of something and hand it to something else, or it can transmit torque from a motor to a driven component. And then it usually has some sort of physical locking feature that engages with some sort of matching feature in the driven component. Basically, that locking feature is what actually does the torque transfer. If I just put a round shaft in a round hole, I can spin that shaft, and it doesn't necessarily spin the thing that's attached to that shaft, right? If I just have a wheel sitting on the ground, it's got a lot of friction on it, and it's got a round hole in it, I put a round shaft in that hole and spin it with a motor, that wheel is not necessarily going to spin, right? That shaft might just spin in that hole. So it has to have something that locks the two things together. All right, so we're going to talk about these two terms, live and dead shaft. So live shaft or dead shaft, and sometimes they're called live axle and dead axle. You'll hear people use both pretty commonly. There are kind of some like loosely accepted definitions for differences between shafts and axles, but when I say loosely, I mean very loosely. In general, shaft and axle are the same thing. Axle usually more has the connotation of being like, a wheel, driving a wheel or some sort of part of a drivetrain, whereas shaft is more generic, but they really refer to the same thing. So when we talk about, live versus dead, live rotates along with whatever it's supporting or driving, right? That is what it is, right? So a live shaft is rotating along with whatever it's driving, and then a dead shaft is only supporting it, right? You think about it, you've got a shaft that doesn't spin and there's a wheel on it and the wheel is spinning. I'm trying to think of a good example of that. Like wheels that you would see like on like a cart that just free roll, like a shopping cart, or maybe a swivel caster on like a big rolling cart like our robot car, or like a desk chair. A desk chair is a little bit of a bad example because those are kind of different the way that they're built, but like some of these big wheels that just kind of free rotate, typically those are on a dead axle. We're not going to talk about dead axle that much. We're going to have a project, I think the last week of the class, where we design something that has dead axle. Dead axle is typically simpler than live axle, like mechanically simpler, and it's also typically very advantageous from a like strength standpoint, but it's a little bit unintuitive. So we're not going to start off with dead axle because it's a little bit harder to understand. And plus, most of the components that we're talking about today are actually, no, not most. Well, most. Most of them are used for live axle applications. So we're gonna talk about live axle stuff today. Pretty much everything we're talking about is live axle. We'll talk about dead axle stuff like later in the class when we're working on a project that actually uses it. So live axle only going forward. All right, so we're gonna talk about shaft, different kinds of shafts. The first type, which is the one that we use the most, is hex shaft or hexagonal shaft. And basically it's a bar that is in the cross section of a hexagon. and the like kind of the corners of the hexagon engage with a hole in whatever it's driving that is also a hexagon. So the hole is a hex and the shaft is a hex. They slide into each other, and because the sharp kind of corners of the hexagon kind of interlock with the corners in the hole, the shaft can't spin inside of whatever component it's driving, and thus it transfers torque. So there's also square shaft. Square shaft is also relatively common. It's used in the Vex robotics competition. Their shafts are usually square. So we don't really use any square shaft, but it's reasonably common. You will not see hex shaft very often outside of FRC and FTC, and in fact, it's pretty much non-existent. Hex shaft is really only a thing in these kind of like educational robotics programs, and there are very good reasons why that is the case. But we're not going to really go into them here. The important thing for you guys to understand is you're going to use hex shaft in FRC, and then you're going to leave FRC and go out into the world and get a job, and you'll probably not use hex shaft again. There might be some applications for hex shaft that should be outside of FRC, but not much. The key thing is it's really easy to use. That's why hex shaft is a thing. It's also very compact in terms of a strength and a packaging sense. So like the shaft, if you think about a hexagon, like a hexagon is kind of like close to a circle. I could have a much more spiky shape, and it would take up a lot more space while having a small cross-sectional area. Hex shafts are relatively strong in terms of torsion because there's a lot of material in this kind of circular region inside the shaft, and that material is doing most of the work in terms of carrying the torque. And so that allows me to have like a relatively small diameter shaft that can handle quite a bit of torque. And then the corners, transfer enough torque. They really don't transfer a lot. Like a hexagon is actually kind of a terrible torque transfer feature. There are definitely shapes that are worse, but hexagon is not one of the best, but it's good enough, right? And the key thing is that hex shaft it's really easy to manufacture a hex-shaped bar, and it's because it's 6 flat faces, which are easy to make, and then it's really easy to make a hex-shaped hole because you just use a tool called a broach. I'm not going to go into what a broach is. We've got one in the shop. I can show you guys tomorrow at our team meeting if you guys want to see a broach. It'll be a little bit easier to explain visually in person, but you drill a round hole and then you use a broach to basically cut the outside of the hole up to be a hex. So easy to manufacture and really easy to put together because you just slide the hex in the hole and you're good to go. And relatively strong and compact, but not high torque capacity. So the one other thing to understand is that in FRC, we typically use something called rounded hex, or Vex calls it thunder hex. And it's essentially just a hexagon-shaped shaft. It's this profile here. And then it's got, instead of having sharp corners, the corners are clipped to form a circle. And so this is a little segment of a circle, this is a little segment of a circle, and these corners all form this circle that goes around the shaft. That reduces torque carrying capacity a little bit, but what it allows you to do is to put it into a bearing. So it still fits in a hex hole just fine. It just doesn't it doesn't fill the corners up, but it allows you to put it in a bearing with a round hole. And that basically just makes it even easier to use. And we'll explain that a little bit more later once we talk about bearings. But so that's a key thing to understand. This center hole is not really important for the shaft. Some shafts have it, some shafts don't. In the case of thunder hex or rounded hex, it usually does, and that has another purpose that we won't bother with right now. The thing to understand, though, is that the material in the center of the shaft does not actually add that much strength. It's mostly the material kind of around the outside that's doing most of the work. So you can put a hole right through the middle of a shaft, and it really does not make the shaft any weaker. So that's something to kind of keep in mind. All right, so keyed shaft. Keyed shaft is based on a round outside profile, so just a very precise round bar, right? Really, really, really easy to make a round bar, and it's also very easy to make a round bar extremely precise, right? Making a hexagon, for example, precise is a little harder. Making a round bar precise is super easy and super cheap. So what you do is you have this little thing called a key, which is essentially just a little square bar of metal, right? This has a, if I cross section this key, it's a square. And then typically they have these little rounded ends, but that's kind of just to make the key a little bit easier to handle. They don't have to have these rounded ends, they can be square. But they're basically just these little rectangular blocks with a square cross section. And you cut a slot in your shaft. You can see here in this image, you can see the slot that goes down the top, and the key just goes in that slot. Now sometimes this slot goes the full length of the shaft. Sometimes this slot is kind of cut into the middle of the shaft and it doesn't extend to both ends. And it usually, the slot at the ends usually has a rounded feature to match the end of the key. So you'll see it both ways, either full length slot or just in one place. It's probably more common to see it just in one little section rather than full length. And then basically what happens is the key goes in the slot and the key is taller than the slot. So the key sticks up a little bit and then you put it in a hole that looks like this, right? It's a round hole with just a little notch out on one side, and the key engages in the notch, and that's how you get torque transfer. So these outside of FRC, these are probably by far the most common shaft you'll see kind of just in general, right? They're in cars, they're in just like little machines that you'll run into, you know, appliances, things like that, industrial equipment especially. You will see a lot of keyed shaft. Because the parts are round, there's keyed shafts are available in this huge selection of different diameters and different materials and all kinds of stuff. And then sometimes shafts will have 2 keys or more keys, like they'll have more keys if they need more strength. But in general, 1 key is extremely strong. And the reason that keys are strong, particularly stronger than hex, is that they have these square corners, right? If I look at a hexagon, right, when it's in this hole, as the shaft starts to twist inside this hole, if it's applying a lot of torque, the kind of slopes of the sides of the hex basically want to like kind of mush the shaft, like mush the corner of the shaft away rather than just transferring the torque. Whereas with the key, you know, I've got this flat-sided notch on both parts, on the shaft and the, you know, whatever's going on the shaft. And that flat side, it doesn't produce any like mushing or you know, doesn't produce a tendency to kind of like damage the shaft. And so basically you have to just straight up shear this key in half in order to fail that torque transfer joint, right? You know, with a hex shaft, you kind of just have to mush the material a little bit. Like think about if you ever use like a screwdriver where it strips out on a screw, or if you've used an Allen wrench, which is a hexagon in a hex hole, how easy it is for those screws to strip. It's the same thing on a shaft, right? But with a key, you've got this square interface, and so it's much stronger. The key thing too is these are also very cheap to manufacture, especially if you're doing a low volume of production, right? If you're not producing millions and millions of units, right, it's pretty cheap to make a keyway on just a few parts. So that's why it's used a lot in industry, especially. All right, so we're going to talk about D shafts and also double D shafts, which are essentially 2 forms of the same thing. Once again, it's a round outside profile, or starts as a round outside profile, and they basically just cut a flat on one side, and the flat can have varying heights, right? And then if for a double D shaft, they just cut a flat on the other side, right? It just starts out as a round bar, and they just flatten the top and flatten the bottom, and it's a double D shaft. Obviously, this has the advantages of starting with round bar, like I mentioned, so you can tap into that really large selection of different diameters of round bar, different materials of round bar, different, you know, heat treating processes for round bar, whatever. And you also pick up the advantage of it being really easy to manufacture very precise round shapes. So you get all of those advantages of a round shaft. And then in addition to that, this flat is significantly easier to manufacture than even a key, right? Like a keyway, the slot is called a keyway. I don't know if I mentioned that, but the keyway is pretty easy to use or easy to manufacture. A flat's even easier, right? This is literally the easiest shaft to make out of all of the different types. The problem with a D shaft is its torque transfer is really bad. Um, this is only useful for very low torque applications where cost is the number one concern. Um, and there's two ways to use a D shaft actually. One is to put it into basically a mating hole that's the same shape or that has that flat. It's not a full round hole, it's actually has the flat on one side. And basically this works similar to a hex where the shaft can't turn because the corners are kind of digging in, and this like little corner here is kind of digging in and won't let the shaft go around. But in order to fail that joint, all it has to do is just kind of round off the material, right? It's like stripping out a hex, except there's only one flat face instead of six. So you can imagine it's not hard to strip out a D shaft. Now double D is obviously twice as good, right? Because it's got two flats, but it's still not even as good as a hex is. The other way to use a D shaft is that you put it in a round hole. These hubs actually look similar, but you put it in a round hole and then you use this set screw on the top. And a set screw is essentially just a screw that doesn't have a head. It's just got a little socket that you can drive with an Allen wrench in it. And it basically tightens down on the shaft, right? You run this screw in, it screws down, and eventually it pushes on the shaft and you tighten it really tight. And basically in order for the shaft to strip out, it has to kind of bend, like kind of push that screw out of the way, which is mush the end of the screw out of the way, basically, or cut a groove through the shaft using the screw. It's like you have to do a lot of damage to spin. Set screws are bad. Like I'm just gonna come out and say it. There are some applications for set screws, and in the right application, they are good. But generally speaking, for torque transfer, you want to avoid them. If you're just locating something on a shaft like left to right, like with a shaft collar, that is where you should use a set screw, or it's acceptable to use a set screw. But in using a D bore and using a set screw for torque transfer is generally something that should be avoided at all costs. Now, that being said, like I said earlier, this has the advantage of being the cheapest shaft like torque transfer interface to produce. So it still gets used quite a bit. You will see this on like very cheap or low speed or low torque like application like appliances and like toys and stuff like that. Very cheap things that need to be able to drive stuff. So a lot of like little cheap motors that you get on like Amazon or whatever, or for little projects and things will have a flat on the shaft because that's what's cheapest to produce. They're also relatively common in FTC. I believe these are FTC parts that I was looking at here, and that the reason that's okay in FTC is because FTC is such a low torque application that the D shaft is okay sometimes. We still use a lot of hex shaft in FTC though, because that's a superior torque transfer interface. All right, so let's talk about spline shafts. Spline is kind of a weird word. Spline also refers to like a mathematical curve. They're kind of related, but not really related. Basically, a spline is where you have like teeth on a shaft, teeth like a gear basically, and then you cut all of those teeth into a hole, and basically all of the little teeth engage with each other when you put the shaft into the hole. There's a lot of variety on what the actual tooth shape is. Sometimes you'll see a spline shaft that's basically just a keyed shaft with a whole bunch of keys around it, like where it's got these square notches. And sometimes, and I should say more commonly, the teeth on the spline are actually a type of gear teeth. I'm not going to go into the differences of what the differences are exactly. The like perfect mathematical shape is slightly different, but basically it's a gear tooth. It's manufactured the same way a gear tooth is, and it gives the best strength if it's a gear tooth. So there's a lot of different standards for different types of splines, but the thing to understand about splines is they are very difficult and very expensive to manufacture. because you're effectively making a gear, right? And gears are common and not super expensive, but they're still not easy to manufacture. They're still kind of expensive. So um, when you have a shaft and you're basically making a very long gear, right? You can imagine that's relatively expensive. So you don't really see spline shafts used for like general purpose stuff. So like if I'm gonna go buy, I can go buy a keyed shaft off the shelf, right? And get it in whatever size I want, and I can buy little keyways, and I can buy a broach to cut a keyway into a hole. By the way, I didn't mention that earlier, but yes, these keyways in these holes are used with a different broaching tool, similar to a hex, but they're very broaching tools for keys are very cheap. It's very easy to manufacture. Whereas making spline shafts usually requires specialized equipment, and it's mostly suited to um, like a manufacturing for a specific application rather than just like general purpose use. You can't really go buy spline shaft stock off the shelf, cut it to length and use it on your robot or your industrial machine or whatever, right? It's usually manufactured specifically for a purpose. So I've got some examples here. These are actually FRC parts. This is the output of the Max Planetary Gearbox. This is a Rev product that I actually designed. We use these like short little spline shafts to engage. Whoops, I accidentally clicked my screen. We use these like short little spline shafts to engage between the stages of the gearbox. Some of you guys that worked on the robot last year probably put these gearboxes together. This is the Falcon 500. This is one of the most common motors in FRC. We don't use them on 3005, so you guys probably haven't played around with them. But they have a spline shaft on the output of the gear, or output of the motor, sorry. And then down here I've got a pinion, which is basically just a word for a small gear. Pinion means a small gear. And you can see on the inside it has these little teeth on the inside of the gear. And basically this gear slides on the Falcon 500 shaft. So those are some examples of splines. You will also see a lot of splines in automotive, right? Because they are doing high volume production for a very specific purpose. So it's not a very big ask to manufacture splines there. The other thing I should mention about the spline is that this is the highest torque capacity shaft type available. Right, the tooth form is optimized to not fail under load. Generally speaking, a spline shaft will just shear right across. You have to break the shaft before it'll strip out. Like you can't really strip them. Not always the case, right? If you got an improperly designed, spline shaft joint, then it'll fail. But so yeah, very, very high torque capacity. You can use very, very strong shaft materials and get very good torque transfer. There's also not a lot of wiggle and slop. I haven't really talked about backlash, which is basically just a word for slop in a shaft. It's a little more complicated than that, but I'm not going to go into that here. Something about how much wiggle there is in a shaft is an important feature of a shaft, which hex and D shafts are somewhat inferior in that regard. They wiggle a little bit more, basically, whereas keyed shafts and spline shafts are very good at keeping themselves very nice and tight and concentric, and there's not a lot of wiggle. So that's another advantageous feature as well. So basically, spline shafts real good, but you will not see them. You will only see them typically in like kind of pre-made products like gearboxes or motors. You will not see like long strips of spline shaft stock that we cut to length and use. That's just not really a thing. All right, let's talk about hubs. Hubs they're not, they used to be super common in FRC and FTC. They are becoming less common. And I'll kind of explain why that is here in a second. But basically a hub is just an adapter. It has a hole in it that slides onto a shaft. Right, it has a hex if it's a hex shaft, keyed if it's a keyed shaft, has a spline, and if it's a spline shaft, whatever it is, right? It's basically a hub. Is basically something that slides on the shaft, and then whatever you want to drive with the shaft attaches to the hub, right? So instead of your wheel or whatever attaching directly to the shaft, you use this adapter to adapt between the wheel and the shaft. Okay. Not all motion components require hubs, right? So if you think about some of the wheels that we use on our robots have a hex hole in them, right? Especially in FTC, right? FTC, a lot of our wheels and stuff have a hex hole in them. So you don't need a hub, right? You just slide the shaft right onto the wheel and you're good to go. Basically, you only are using a hub, it's at least in FRC, where you want flexibility on what type of bore, right? So like if I have a wheel, right, and it has a keyed bore in it, right, I can't put a hex shaft in that, right? The wheel has a keyed bore in it, like I'm done, right? I'm out of luck. So it's better usually to, make your wheel with like a big hole in the middle and then use a hub that attaches to the wheel that has the shaft hole in it. And then typically the hub is cheaper to replace than the wheel. So you keep the wheel, you keep the hub, you use whatever hub you need, and you can swap them out, when you want to change shafts. We showed some pictures. Some of the pictures that I had in the previous pages were hubs, but I'll show a few different types right now. So here's some examples, and I tried to kind of do some examples of ones that pair up. So the hubs can have a little bit more, fancy features. So you can have hubs where they have some sort of interlocking feature. Best example is this one over here. These are called Max hubs. This is a product I helped design at Rev. It's brand new. They have this kind of like flower petal shape, which is technically a spline. It's called Max spline. And then basically it goes into a wheel that has the similar thing, and then you use screws to clamp it in place. But the screws aren't transmitting torque. The actual outside spline of the hub is transferring the torque. And then you can get these hubs in different materials and different bores, and it allows you to use the same wheel but change, what type of shaft goes through the middle of the wheel. This over here is a hub from Vex. Basically, we use some of these. Basically, you have kind of two torque transfer features here. So you've got these little nubs on the wheel, and they engage in these slots on the hub, and that helps transfer torque. And then you've also got the bolts where if the hub wanted to strip out, right? If the hub wanted to strip out of the wheel, you would have to shear the screws. You have to break the screws, and the screws are going all the way through the wheel and but basically just bolting this hub to the wheel. You can get these in different materials and different bore types, right? Same concept as any other hub, right? You want to use the same wheel and you want to change what bore type it has, use a hub. We got some other hubs here. These are some hubs for FTC wheels, right? They have a smaller hex and have some holes. This is a hub. I think this is from AndyMark. It works similar to the Vex one, except it doesn't have the little slots. So this hub here is only transferring torque through the bolts. So real quick before we move on, I just kind of wanted to talk about hubs. I mentioned at the beginning that they were becoming less common. The reason that hubs are becoming less common is it is typically lighter weight to have just, have a wheel that has a hex hole in it. In FRC at least, teams have pretty much solidly standardized on hex shaft. Even, well, I say this, but it actually sounds like a long time. 10 years ago, right, which doesn't feel like that long ago, but I guess it is. 10 years ago in FRC, hex shaft was not nearly as ubiquitous as it is now. There were teams using keyed shafts. I mean, I remember most of the shafts on the robots I was building as a student, had a lot of keyed shafts there. There was not necessarily a lot of hex. There was some, but not a lot. And so hubs were a much more desirable feature in FRC back then because you needed the ability to kind of switch what bore type your wheel had, right? You didn't want to buy a wheel that had a half-inch keyed bore when you were using a 10 millimeter keyed shaft or whatever, right? You needed the ability to change. That is not so much the case anymore. Like pretty much everybody uses hex, half-inch hex. And so, manufacturing your wheels with half-inch hex in them is becoming more common. I mentioned the product that I worked on at Rev that has the Max spline in it. One of the things that we did was we made the hubs really, really small. So to kind of mitigate the weight penalty of having a hub while still getting the flexibility. So that was kind of an important feature. But there's a decent number of wheels that have direct hex, especially smaller wheels. It can also be cheaper if you have a smaller hub or if you have no hub. Those are just all advantages. Now, one thing to note there is outside of FRC, hubs are still very much alive and well. If you go into industry, you go into industrial machines, or even in automotive and things like that, you will use hubs a lot. So it's a good thing to understand the concept of a hub and get used to how hubs work and what they're supposed to do. There are also different other kinds of hubs. There's hubs that clamp to shafts and things like that I'm just not going to talk about because they have just no use in FRC. But just something to be aware of is there's a lot more out there when it comes to hubs, and it will become important if you're working on non-robotic stuff. All right, so let's talk about bearings. Basically, I tried to come up with my own definition for bearing that was a better explanation, but really this little snippet from Wikipedia was pretty much said it pretty well. It's a mechanical element that constrains relative motion to only the desired motion, and then it also reduces friction between the moving parts. That's a little wordy, but I couldn't really improve it at all. So there's basically two key things here, right? You have some motion that you want, right? It could be rotary motion. Usually it's rotary motion, but it could be linear, right? It could be sliding back and forth. And you want that motion to occur, and you want that motion to only occur, right? You don't want any other motion, right? If I've got a pivoting shaft, I don't want that shaft to wobble back and forth. I want it to just pivot, right? I want it to spin, right? And so a bearing constrains moving parts to only move in the way that you want them to, and then also reduces the friction between moving parts, right? If I just take a shaft that's spinning, in a hole, and I just drill a hole in a material and stick the shaft through there and spin it, right? There's a lot of friction there. That friction is going to slow my mechanism down. It's gonna make my mechanism less efficient. It's gonna sap energy from the system, and then more importantly, it's gonna generate a lot of heat, and it's gonna wear out my parts. Right? If I just have two things sliding against each other, I need to reduce that friction. So I mentioned there are linear bearings. I will talk about those briefly at the end of this, but most of them are rotational. In FRC especially, we use mostly rotational bearings, and if we do linear systems like elevators or slides or whatever, we kind of have like special things that we do to create that linear motion. So I'm not going to go into that very much. Couple little terms that we need to understand. Usually a bearing constrains a shaft, right? We're talking about rotational motion. It constrains a shaft in the radial direction. So radial is basically like outwards away from the shaft, right? So if I have a long skinny shaft, right? You think about an axis, right? Going through the center of that shaft, like along the shaft's length. That direction, like along the shaft's length, along the shaft's axis, is called the axial direction. And radial is basically any direction facing out from the shaft, like around the circumference of the shaft, right? Away from the shaft. That's radial. So radial and axial are important to understand. Axial is along the length of the shaft, like along that central axis. Radial is radiating out from the shaft, like circumferentially. I don't know if I said that right, but whatever. Okay, so usually you're constrained, you're worried about the radial direction. There are some bearings that are specifically focused on supporting axial loads, which are typically called thrust loads. So thrust and axial loads are basically the same thing. But a lot of the most common bearings basically do both, right? Just for convenience. So we're going to talk about some of those. So first of all, let's understand the difference between what is called a plain bearing and what is called a rolling element bearing. So a plain bearing is often also called a bushing. Now this is a little bit of a pet peeve of mine. A bushing is, no, let me back up. Actually, I'll explain this in a minute. Let me move on. Okay. A plain bearing is basically just a one-piece bearing that is made of a low friction material, and basically it's just a part with a hole in it made of a low friction material that your shaft just goes inside. So there's no moving parts. It's just basically a slippery material that does not create a lot of wear, and your shaft just kind of spins inside that material, right? That is a plain bearing. Plain bearings can be made of like a huge variety of materials. Um, they're typically metal or that is particularly slippery. We'll talk about some different types here in a second. Metal that's very slippery, or plastic that's very slippery, or like in some special, like very intricate mechanisms, like expensive watches, they actually use jewels like rubies, or I think amethyst might be one that they use a lot. But they use these gems. Sometimes they're lab grown, sometimes they're genuine, and they use those because they're so hard that they don't wear out, right? And so there's like all kinds of materials you can make plain bearings out of. Cast iron is a relatively common one. There is a giant area of engineering that just goes into bearings. Like, it is a huge area of engineering. There's all kinds of research and special things that are done to bearings. It's crazy. To be honest, I don't actually know that much about it, more than the basics. So, but the good news is we only have to know the basics for FRC. So a rolling element bearing is a little different than a plain bearing. It's got basically rolling objects that basically roll between two round surfaces. And because the objects are rolling, there's no sliding motion. Like with a plain bearing, there's always a sliding motion. Now, it's a low friction material, but there's still sliding. There's still some friction. And so rolling element bearings basically they're typically balls, like metal balls. Like, you guys have probably seen ball bearings. Just very, very precise, very, very hard round metal balls, or very, very precise, very, very hard round cylindrical pins. As a different type. We'll talk about the differences between those. But basically, you've got two surfaces, and these round shapes roll between the two surfaces as the two surfaces spin inside of each other. And that's very low friction. It's a little more complicated, takes a little more space, costs a little bit more money, but it has lower friction. So we'll go into more detail here in a second. We're going to start off with plain bearings, though. Okay, I'm going to have my rant about bushings now. Now that I got a picture on my screen. So this is a bushing, or I should say, this is a bronze plain bearing. And typically, a bushing is a very generic term for a very generic shape where it has a large outside diameter and then a small outside diameter, and it's basically used to adapt from a large hole to a small hole. Right? That's basically all a bushing is. There are bushings that are not bearings. Basically, all plain bearings are a form of bushing in some way. However, not all bushings are bearings, if that makes sense. There's a Venn diagram, right? And plain bearings are inside of the bushing circle. Bushing is a bigger circle. There are things that are not bearings that are still bushings. One of the best examples is in pipe. There's a pipe fitting that's called a bushing, and basically what it does is it reduces from a larger diameter pipe down to a smaller diameter pipe. There are other types of bushings. There are bushings in the spindles of CNC lathes used to adjust for what size of material you're feeding it. There's other types of bushings that are not bearings. Now, you will hear a lot of people say bushings. I will say bushings. It's a very easy term to say, but it's just something to understand is that that term is often used slightly incorrectly. It bothers me a little bit, but it's not actually that important. If you say bushing, people will usually assume you mean plain bearing, and if you hear somebody say bushing, they usually mean plain bearing. So, rant over. We're going to talk about something called oilite. Oilite's a brand name. It's basically a special type of bronze. It's sintered, which basically means it's powder, and then they press the powder using a press, but they don't press it all the way, so there's still like pores in the powder. You can kind of see all these parts on my screen have this kind of like speckled texture. It's a little bit hard because these pictures are not that high resolution. I couldn't find better ones, but they kind of have this speckled texture, and that speckling is the little pores in the bronze. So bronze by itself, even without this particular structure, bronze is a very slippery metal. Typically, the copper metals typically make pretty good bearings. Bronze, brass, even pure copper by itself, they're all relatively good in terms of bearings as being low friction. So you'll see a lot of what is typically called red metals, which is basically just copper alloys like bronze, copper, or pure copper by itself, brass, whatever. You will see a lot of red metals being used for bearings because they're very good for it. However, this oil light kind of takes it a step further. They basically, when they press the powder, they trap oil in these pores. And so what happens is, as the bearing runs, as it heats up, as it wears, these pores kind of open up and it lets a little bit of oil out at a time. And so basically it's referred to as self-lubricating, right? You don't have to apply oil or grease to these to get them to run smoothly over a long service life. You can kind of just put them in, they'll lubricate themselves as they run, as they wear, and you never really have to worry about it. Sometimes they put graphite in there instead of oil in case you need, something without oil in it for certain applications. These are very cheap. They're widely available in a lot of different sizes. They're very small. They don't weigh very much. They fit in tight spaces. They're very small, so they also don't weigh very much. And they are good at handling very high loads because there's a lot of surface area, but only at low speed. They're very susceptible to high heat. So if you try to run these at thousands of RPM, you're going to have a bad time. You'll see some features here. You'll see these flanges on some of them. That is an extremely common feature of bearings. We're going to talk a lot about flanges, or you'll see a lot of flanges as we get through the rest of this presentation here. Flanges, basically, if you've got a hole, you can push the bushing or the plain bearing into the hole, and the flange just stops the bushing from falling out the other side of the hole. So that's the purpose of a flange. They're very common features to get, bushings or bearings with flanges or without. This guy right here is basically just a washer. This is typically called a thrust washer. It's also oil light. It's also bronze, but this is used for only supporting axial loads or thrust loads. So this is an example. This one's mostly for radial loads. This one's for thrust loads. You can combine the two and use them for both. Coincidentally, the flange also can act as a support for thrust loads. That's another use for the flange. Okay, let's talk about plastic bushings. Basically the same as a bronze bushing, except it's just solid plastic. It's typically made out of something very slippery. Delrin is a brand name for a plastic called acetal or POM. Those are all the same thing. Delrin, acetal, POM, they're all the same thing. Those are typically a good bearing material. A lot of plastic plain bearings are made out of that. There's other plastics available that work as well, like Teflon works well. There's other things that are also good. Basically, this is the cheapest type of bearing you can get, really. It's the lightest weight. Bronze is relatively dense, even if it's porous, it's still relatively heavy metal. So even though they're very small and light, they still weigh more than plastic does. These are good for really light load applications at low speeds, right? It's plastic, it really can't handle any heat, and it's also, not that hard, so it can't really handle a lot of load. But they're really good for small, cheap applications where you need them. So plastic bearings are really common. You can get them with flanges, you can get them without flanges. Not much to be said here. We don't use a ton of them in FRC because they are typically they can't handle the speeds and the forces that we're dealing with, and the cost savings is not really worth it. Bearings in general are very cheap. There are obviously expensive types of bearings, but in general, bearings are pretty cheap, and so it's only the cost of a bearing only really matters when you're like producing like millions and millions of units, or you need to like really get a cheap product. So like you'll see them a lot, like plastic plain bearings, especially you'll see them in toys and things like that, where it's like every tiny little fraction of a penny matters. All right, so let's talk about radial ball bearings. Now this is not a plain bearing. This is a rolling element bearing. Typically, a ball bearing, most bearings, but ball bearings especially has several features. They have this outer part. You can see it here. You can see the outer part has a flange on this bearing. These bearings down here, the outer part does not have a flange. This outer part is called the outer race, as in like raceway. And it's basically got a groove on the inside that you can't see. And then the balls, these are ball bearings, right? The balls that are inside the bearing basically roll in this little groove, and that groove keeps the bearing from coming apart sideways. Then the inside of the bearing, there's another inside piece, that's called the inner race, and it also has a groove on it, and basically the balls roll in the groove, so the bearing kind of holds itself together. So they're also called, most common type of radial ball bearings are deep groove ball bearings. It's kind of just like, I don't know, it's just a normal bearing, like in air quotes, like it's just a normal bearing is generally a deep groove radial ball bearing. Generally speaking, the inside of the bearing is round, but you can get ones like, for example, this one over here is hex. This is a bearing used in FRC. It's got a hexagon in it. I mentioned earlier the hex shaft that had the rounded corners. That's nice because like with this hex bearing, you have to like when you're assembling a mechanism with this bearing, you have to like wiggle the shaft around and try to get the corners of the hex to line up before you can slide the shaft through this bearing. Whereas if you have the hex that has the rounded corners, you can just put it through a round bearing and you don't have to care about the orientation of the hex. And so it makes the hex or the shaft way easier to assemble. There's a couple features of bearings. This little graphic down here is really great to emphasize. There's basically three distinct types of bearings. There's what's called open, which is where the sides of the bearing are open, and those are, those can run very fast. They keep themselves cool because air can get in the bearing. So typically the highest speed rating bearings are going to be open. This next type in the middle is called shielded. These top two are also shielded. It's basically just got this metal cover over the side. The metal cover does not seal the bearing, but it keeps dust out. Give me 1 second. I think I just lost my headphones here. Give me... there we go. Okay, I think we're back now. RoboCharger students, if you guys hear my like you hear like background noise or anything, let me know. Or if I'm back to sounding like I'm on my headset, that's good. Okay. Anyways, shields. Shields keep dust out, right? They don't seal the bearing. There's like liquid and stuff could still get into the bearing, but dust and just general dirt stays out. So generally speaking, the shield is pretty low. Like it doesn't add any friction to the bearing. It keeps enough dirt out. This is what we typically use in FRC. You can run them at very high speeds. They still stay relatively cool whilst keeping themselves clean. Right, driving around on carpet in FRC, you would not want an open bearing. That would go poorly for you. This last type is sealed. Unfortunately, sealed is actually one of the most common types, which is a little bit annoying when you're trying to get bearings for FRC. Sealed bearings are exactly what they sound like. They have this rubber seal. The seal adds friction to the bearing, so they're typically not that great for high-speed things. But they do keep liquids and other things out, and you can get bearings that are like airtight, so right for rotating pneumatic applications or whatever it is that you need. But yeah, typically the reason why you have a sealed bearing is it keeps lubrication in and it keeps outside things out, and just nothing can get in there. Those are very common. Unfortunately, they're not super great for FRC because they add a lot of drag to high-speed shafts. So that's kind of unfortunate. Generally speaking, these are the types of bearings that can handle the highest speeds because they're good at rejecting heat and things like that. And they can generally handle pretty high load as well. I describe them as medium load, right? They can handle probably less load than like a bronze bushing can, but they can do a medium load at a higher speed. They're also produced in such high quantities that they're very widely available. All right, getting on to our last slide here, one of our last slides. All right, roller bearings are a different type of bearing where they use these little round pins. And basically what these round pins do is they roll the same way that the balls in a ball bearing do. However, because there's more contact surface area, because the pins are long and skinny, these can handle higher loads. They can handle higher loads at the expense of being at slightly lower speeds because there's more contact area, more heat buildup, and they can build up heat and fail faster. Because the little pins don't really work side to side, they only work in the direction they're meant to roll. These bearings do not provide any axial or thrust load. Like it's only radial. It's no axial load, no thrust load support. And so typically you have bearings like this that handle axial load, and then you actually have a different version of these bearings where these little kind of washer-looking things with little pins in them um, uh, handle thrust load. And so the other feature of roller bearings, which is kind of strange, but is pretty common, is they don't have an inner race, or they have an outer race, but they don't have an inner race. Or in the case of this thrust bearing, these rollers are actually exposed on the back side. It just rolls between two surfaces. Or in the case of this bearing up here, you put a shaft through this bearing and it just rolls on the shaft. Um, so basically, that saves space, right? The inner race adds diameter. So having it roll directly on the shaft saves weight, but it does mean you have to have usually a precision ground shaft or something very precise. We used these bearings similar to this on our launcher, our shooter for our robot last year. You know, we cut some corners there and had some issues with the bearings, but generally you can make it work. Using roller bearings in like an industrial application is typically a much more involved design process, unlike how we use them. The small sizes that we use in FRC are typically called needle roller bearings because they have very small rollers, but there are bigger types of roller bearings. There are also special types of roller bearings that can handle radial and thrust loads. Those are the types of bearings that are used on the wheels in your car because they can handle very high load, right? Your car going around corners and going over bumps and stuff. Those are called tapered roller bearings. They have no use in FRC because they're usually very large and very expensive. But that's what's used on cars usually. All right, I want to briefly touch on linear bearings. Not really common inside of FRC, but you see them sometimes. The most common things you'll see them on is like CNC routers, CNC mills, 3D printers, things like that. Typically, you got some sort of rail. This bearing up here runs on a precision ground round rod, right? That's very cheap. These are the types that you usually see in 3D printers. Basically, these ones down here have these kind of like weird train track looking like kind of T-shaped rails, and basically they just have little balls in them that kind of go around and around and around this little track, and it provides this very smooth linear motion along whatever rail it is that they run on. These are very cheap. There's the more precise you get with these, the more expensive they get, especially if you get large, they get expensive very quickly. But very small ones like you see in 3D printers are usually pretty cheap. These rail types down here are significantly more expensive, but you can also find some low cost ones in some small sizes. These are good for like projects and things. A really easy way to get precise linear motion. Outside of FRC, these are not super common inside of FRC, but outside of FRC, mounted bearings are kind of like the king. You generally want to just like have a bearing with some bolt pattern on it, and you can just bolt the bearing to things. In FRC, we usually fabricate or cut precise holes in parts, and then we press bearings in. We do that because that's lighter weight, it's cheaper, and it takes less space. But outside of FRC and more industrial applications, the convenience of having a mounted bearing is worth paying more, having a lot more weight. These housings are cast iron usually, so they're very heavy. But the convenience of being able to just bolt it in place is super nice. Some bearings, usually like this one, you can kind of see these holes are slotted, so you can move the bearing back and forth, which is good for getting alignment. In addition, bearings like these usually, this central housing swivels a little bit, so the bearing inside of this big housing actually swivels, and that allows you to kind of account for shafts that are not quite aligned, and that's handling that misalignment is really important in industrial applications where you got stuff that's running for very long periods of time. These are usually bigger. It's hard to get mounted bearings in a small size, so they're usually very large, like an inch diameter shaft or larger. So that's another thing as well. That's another reason why they aren't typically used in FRC, because we're usually using much smaller shafts, and you can't really find mounted bearings for those small shafts usually. All right, I ran over a little bit there. I tried to go as fast as I could on the first segment because I knew the second segment was going to be long. Shortening this class to 10 weeks instead of 16 weeks, which is the way that I taught it last time I did this a few years ago. shortening it to 10 weeks kind of took a lot. I had to combine some stuff into presentations like this one where I'd normally handle them separately. Bearings would normally be a presentation all on its own. So sorry we went over, but we still got plenty of time for CAD. Any questions about bearings, shafts, hubs before we wrap up here? Don't see anything. Don't see anything. Any questions in the chat? Thanks for the heads up on the sound. It's good. That's working fine. Let's see. I got a notification here. Dope. Okay, so if there's no questions, you guys can always ask in the YouTube chat if you're watching this video after it already was live. Robocharger students, you can ask, in the channel in our Slack. Anybody tuning in from Chief Delphi, you guys can ask questions in the Chief Delphi thread. Basically, you know how to reach me. There's a lot of different ways. I'm going to be live at my computer until for the next about 45 minutes as we kind of wrap out our class session. So I'll be answering questions kind of right on the spot if anybody has any questions. For now, we're going to go into our CAD session. So basically, I shared a link to the pre-recorded CAD video for this week. As usual, you guys should just take that CAD video and over the next like 45 minutes or so, you guys should kind of follow along in that video. That video is about 45 minutes, so you probably need to spend a little time outside of the class session finishing that up. But basically, now's the time to do that. I'll be on the call or available and for questions if anybody has any. But I am going to end the YouTube stream now. So thanks everybody for tuning in. We'll see you guys next week.